Hey YouTube, this is Austin with Austin'sLearningThings.com. Today we'll be picking up with part 2 of our building a autopilot in XPlane using Python. So we left off with the last episode with connecting up our code to XPlane. I basically picked it up and just started running it again. So we're spitting out our latitude, longitude, altitude, and the controls. So I'm going to go ahead and stop that. The first thing we're going to tackle is how fast this runs. So this loop runs basically as fast as it can, which sucks down a lot of CPU, and it also means it's running more than it has to. Control loops, depending on what you're doing, don't typically need to run thousands of times a second. For my remote control plane, for example, that uses RGPlane on a Pixhawk, it has an update frequency of 50 Hertz, which is 50 times per second, which means that there are 20 milliseconds between each update interval. Really anywhere in the 5 to 100 range is workable. We are going to target an update interval of 10 Hertz, that would be an update frequency of 10 Hertz, and update interval of 100 milliseconds, or 0.1 second. So that means we basically need to make this loop not run. At least the code inside of the loop we need to not run if we are not past the right time for that. So we're going to need some timing things in here, which means we are going to import from datetime as well as time delta, because we'll be using the difference between the execution of the loop and the, basically the loop will run, we'll check, is the time greater than the last execution plus our update interval. If the answer is yes, then it will go ahead and run the code of the loop. If the answer is no, it will basically skip out and say, we don't need to do anything, just skip. Okay, so we've got our stuff in here. We're going to say the update interval is equal to 0.100, and this will be in seconds. And the start will be equal to datetime.now, which means as soon as this line gets executed, it's going to assign now to start. And then we're also going to say last update is equal to start. These are basically the two variables we need. We only really need one for inside the loop, but to kick it off, we do need the extra, at least with how I'm doing this. So with that, we can start our next portion. So inside the loop, while true, we're going to be checking. So if right now, datetime.now is greater than the last update plus the time delta, the difference in time, basically between last update and now. So we're going to say milliseconds is equal to update interval times 1000, because this we need to get this into milliseconds. So like I said earlier, if this just checks if now is greater than the last update plus our time difference. If the answer is yes, we are going to run the code. If the answer is no, we don't need to do anything about it. And so, okay, I need to change all of these to tabs, because I like tabs. Alright, so with that, we can also, with that, we also have to define when the last update was with every loop. So the last update will be datetime.now. So if it runs, say the last update is now. And then with this, we can print out a statement showing us when these are running. We'll do print, we'll do F for, I think it's called interpolated strings. So we'll say loop start, and then datetime.now. Okay, and then this is the rest of the code from last time. So if we go ahead and hit run on this, alright, I forgot to add the other thing in there. We need to define last update as a global. And then we can run it. Alright, so loop start. You can see here that we are executing this far less frequency than we were. So if we pause this, you know, just looking at these three here, is at 302 milliseconds, 402 milliseconds, 503 milliseconds, which means, you know, the loop duration is, this could be fine-tuned, but this is close enough. It's basically 101 milliseconds, even though we define it to be 100. So that's fine. Okay, so that's number one. We have our loop running at an update frequency of 10 hertz, which means an update interval of 10 times per second. What's next? What's next is to actually add some controls. Alright, so we are going to dive into the control theory aspect of this now. What we need is this file called pid.py. I'll put a link to it in the description, as well as in the blog post. Basically, let's see, Mechatronics Limited wrote this. They provided it for free with the GNU General Public License. And so this, I found a lot of sources, they reference this. And so I said, okay, let's just use this. Basically, a PID controller, in a nutshell, is a method to achieve a set point by altering outputs. And so P is proportional. You know, let me just open up the Wikipedia here. And let's see if there's anything we can scroll through. Not really. You know, I'll probably just cut this out. Alright, this will actually work. So for pseudocode, what it does with each loop is it gets the error between the set point and what the value currently is. The proportional is equal to the error if p equals 1. Proportional is typically scaled to be some factor of the error. The integral is the previous integral because it's an integral plus the error times the difference in time. And the derivative, you know, these are just calculus type things. Then the output is sum all these things up, set the previous error, and then weight some portion. And so, you know, we're waiting 100 milliseconds on here. And so this is what we will be using for the PID controller. They have defaults of P is equal to 0.2, I is 0, D is 0. And so what this P equal to 0.2 means, basically that means if it set the proportional portion of the PID controller equal to 20% of the error. So if the error is, you know, 10 degrees, the proportional output will be 2 with 0.2. And so this is where you tune for the rapid response. This is the main tuned figure, the P. I is the integral. It takes care of longer term errors. And D is essentially what you would set to look ahead and see what you will be getting at the set point and adjust the output based on that. There are far more PI controllers using just proportional and integral than there are PID controllers. You know, most of these, when you buy them off the shelf for control type things, you have the option to set all three. All of them basically will use P. A large portion will also use I, and then not that many will use D. I think it really has to do with motion more than, you know, temperatures and tank levels and things like that. So we'll get that file. You have to put it in the same directory as the rest of the stuff here, and then from there we will use import PID, so we can use that code that we have just obtained. And so the first thing that we talked about doing is a wing leveler, which is basically setting the roll to 0. You know, we want the wings to be flat. We want the horizon to be flat. We want the ground to be down and the sky to be up. So let's go ahead and define a roll PID. Roll PID is equal to our new PID and then a new instance of PID. And we can leave these values, but typically it's better to start with smaller values than larger values. And so we saw the default is P is 0.2. We're going to use a value of smaller than that. We'll do 0.1. So we'll say P is equal to 0.1. I is typically some fraction of p. We're going to use p divided by 10. And then d will be 0. So p, I, d, we will use our values there. And we will also do a pitch PID at the same time. We can keep the wings flat, the horizon level, but unless we also define our pitch, we could have the sky be down and the ground be up, which is not what we want. That means you're upside down. So let's do pitch PID is equal to same thing. Thing about these is they are often quite adaptable with just simple values. These work in many cases. It's surprising how well these work for almost all circumstances. So next up we want to define our desired roll, 0. That means we're wings level. Desired pitch will also be, actually we're going to make this like 2 degrees, because if the plane's flying with a pitch of 0, it's probably losing altitude, angle of attack and all that. So, alright, and then we need to set the set points on these PIDs. So we'll do roll PID dot set points down here is equal to desired roll, and pitch PID dot set points is equal to desired pitch. Okay, so we have our PIDs initialized. We have created some values in here, and we have set the set points for those PIDs. Let's see, what else do we need? We need to get some data so that we can feed the current values into the PID loops. So, let's see here. So we still have the position, we still have the control values. What we also want to get out of the position is the current roll and the current pitch. And so those happen to be the 5th element and the 4th element in posi. So, like I said, these aren't super well documented in trial and error. That's what we got. Okay, so with the PIDs, we have to feed it the current value for it to do its magic and to get the output value. So what we're going to do is set the, we're going to update the PIDs. So we're going to do roll PID is going to be updated, update with the current roll value. Same with the pitch. Okay. So these now have an output value, and before we do anything, we should start thinking about how to visualize this stuff, and we will make the graphs eventually, but for now we're just going to output to the screen. Alright, so I'm just going to copy and paste this line in from the notepad that I'm using over here on the side. Alright, so I truncated it a bit here because it's using some variables we have not defined yet. Okay, so this is just going to tell us, spit out what the current roll is and what the current pitch is, and assign to the variable of output. We're basically going to create a number of, we're going to concatenate strings to spit it out once at the end. So we'll do output equals output plus a new string. We're going to see what the output of these is as we're flying. So roll, let's see, what do we want to call it? PID outputs. Then we'll do roll, will be roll PID dot output. And then, okay, so this, dots, or space 0.3f is a rounding thing. It just makes it look better. So you don't have super long values hanging out at the end. We really don't care about the stuff past a couple decimal points. Okay, so that's going to be the roll output, and then we also want the pitch outputs. Alright, so this will, well, let's run it, see what happens. And we are not actually printing output yet, so nothing is getting written. So let's print it. Okay. And then we will do one extra thing to make it a little bit prettier. Output is equal to output plus /n, the new line, so we get a break here. Alright. It looks like I also need to add the /n up here. It's equal to output plus /n plus that. Okay. So that should do it. Alright. And then if we want to line these up, we can. Let's see, that's going to be 1, 2, 3, 4, 5, 6. Looks like 1, 2, 3, 4, 5, 6. This is super unnecessary, but it helps space things out. Okay, so we got the roll lined up, and then we are going to also get the pitch lined up. That's going to be 1, 2, 3, maybe just 2. There we go. Alright, so with that, so our current values, we are rolling to the, the wings are to the left a little bit by 1.3 degrees. We are pitched about 2 degrees down. And so the PID is feeding a little bit to the right and a little bit up. So that looks like what we want. So with that, we can feed it new control values. Alright, so let's say new airline control is equal to, we're just going to set it right to the output. And then new elevator control is equal to the output as well. And then the controls, I'm just going to copy and paste this also from the notepad. So the controls are in this order: elevator, airline, rudder, and throttle. 999 negative 998 means don't change. So we're going to say negative 998 for throttle because we have not done throttle yet. Alright, so we should be good here. I'm going to take off and get flying, and then we are going to start running the code and see if it levels us out. Alright, cross your fingers here. Let's see what happens. Alright, release the brakes. We're flying. I'm not running the code right now because it would start, it would fight me. And I don't want code fighting me because it's 2:17 in the afternoon, so that's late enough. Alright, we're off the ground. G for gear up. And we're climbing with full throttle. Alright, so now we're going to come over here and hit F5 and run the code and see what happens. Okay, well, what happened there? Are we flying exactly where we want to be? Kind of. We see these values scrolling by. We have roll of, a 100th of a degree to the left, decreasing. Pitch just got above 2. If you recall, we did set this to 2. And it looks like it is stopping at a value here. So 2.0, 2.1 degrees instead of 2 degrees. We are flying straight and level. This is our, we're calling it the wing leveler. And it's level, ground down, sky up with these exact values we want. So let me stop this, and then I will try to bank us a little bit and get us into a funky position, and then we'll kick it off again. Alright, ready? Go. Look at that. Still a little to the right, but it's coming back. Pitch, coming back. This is with basically defaults. I said it's better to be slower than faster, and it's pretty fast. That's snapping real fast. If you recall, the default for P is equal to 0.2. We're using 0.1, and we're just using 1/10 of P for I. And so that's why, you know, this pitch is slowly getting to the right value. Even though we're getting closer to it, the PID output is increasing because that's what the integral does. It takes care of the long-term effects. Actually, let me set this to 0, and I will show you what happens when we have no integral portion of this. Alright, we don't need to get super crazy. Okay, so we're doing this banking descent again. Turn it on. Alright, so let's see what happens with roll and pitch. Roll is stabilizing at 0. Pitch is not. Pitch is going the wrong direction. We want it to be at 2. Pitch is decreasing. So what the integral portion of the PID controller does is it takes a look at this and it integrates the error over each iteration of the loop. And if the error is not decreasing, then it gets fed into the control algorithm and essentially says, okay, we need to bump this up a bit because clearly just this proportional portion of this is not doing it. Alright, so let's see, we're going to level out at 1.52 degrees pitch. So I'm just going to stop this, and that's not what I wanted. F11 is typically full screen. Okay, so we're going to set this back to P divided by 10, and we'll see how quickly it gets to 2 degrees. Okay, so see we're here again, but now it's getting closer to 2. 1.7, 1.8, 1.85, 1.9. Creeping towards 2. Creeping. 1.96. That's basically close enough. It will get there. I have weather totally turned off. 0 wind, 0 clouds, 0 whatever. You know, build things in an ideal world first, and then add in the non-ideal factors. So as you can see here, we're not rapidly. We are closing in on 2.000 degrees. And that's what the eye did for us. So this is at this speed, 170 knots. You know, we're slowly gaining altitude. If I had this set to 0, we would be losing altitude. Again, that has to do with the angle of attack. Oh, hey, here's Denver International Airport coming up right here. Let's see, where's this at? Yep, that's DIA flying kind of over the C terminal. C terminal will be right about here. So, in case you're wondering how long it would take to fly from Broomfield to Denver, about 170 knots. It is the time to record a video on implementing PID controls in XPlane using Python. So we have leveled the wings. The sky is up, the ground is down. With, you know, this isn't really that many lines of code. 52 total. Let me see how many were from the original. 52, 15, so that's what, 37 lines of code with spaces to get to our pitch roll autopilot. So that's really not bad. You can do a lot in Python with a little, which is what I like about it. So we could add the throttle PID control next, which is probably what we'll do. And we will tackle probably both heading and altitude. Essentially, we will be putting loops inside of loops. We have the outer control loop and the inner control loop. You know, if you want to get to an altitude, you don't control the elevator directly to get a pitch. You know, these are two separate things. Altitude and pitch are two separate things. So we'll get there with the next episode. Hope you learned something today. If you have any questions or comments or like what you learned, go ahead and click like and subscribe. And we will be doing another one of these by the end of the week. Alright, thank you very much. Thanks for joining.